In this lecture, I'm going to talk about analytic functions and the Cauchy-Riemann conditions. And analytic functions are pretty straightforward. An analytic function, f of z, is analytic if its derivative with regards to z is well defined. Now, this isn't trivial, right? Think about it. You have the Argand plane and you've got some point z on this Argand plane, and you're calculating the value of this function at that point z. You could calculate the derivative f with regards to z, but z is a two-dimensional object. In other words, you could calculate the derivative of z in this direction, in that direction, in that direction, in multiple different directions. And what this is telling you is that f of z is analytic if you calculate the derivative in all the directions and they all agree and give you the same value. So let's simplify this a bit and let's consider two different directions, okay? Let's consider taking f of z, okay, and we can write it out in terms of its components, okay? And let's take the derivatives along, take derivatives along the x direction and the y direction. Okay? So let's do this explicitly. In fact, let's use the definition of the derivative that you learnt when you first learnt about derivatives as a limit. So along the x direction, we have that it's the derivative, and I've written z in terms of its components x and y, and I'm doing the derivative along the x direction, and we take dx to be small. But now we can replace our definition of f in terms of u and v, and if we plug it in, what do we get? We get the partial derivative of u with regards to x plus I, the partial derivative of v with regards to x. Okay. Now let's do the same thing but along the I direction. Okay. Now we take, and I should have done this here, the limit when dy goes to 0, and now we have f of x y plus dy minus f of xy along the I dy direction. And if you do that, what do you get? You get 1 over I du dy plus you get an I from the dv dy, but it cancels with the y on the bottom, with the I on the bottom, and you get dv dy. Okay. Now, if these two things are going to be equal, then we have that these functions, the derivative of these functions, have to satisfy the following condition. Du dx equals dv dy, i.e. that has to be equal to that, and du dy has to be equal to minus dv dx. Why minus? The I on the bottom here, I on the bottom here, I on the top here. When you flip this up, you get a minus sign, and you're comparing this to this. Okay. These conditions here are what is known as the Cauchy-Riemann conditions. Okay. And basically, a function f of z is analytic if its component functions satisfy the Cauchy-Riemann conditions. Now, it's interesting that we can obtain the Cauchy-Riemann conditions simply from the fact that f of f is a function of z alone. So, f of z basically implies that if we take the derivative with regards to the conjugate, that's equal to 0. Now recall that you can write down the conjugate, and it's x minus iy, which means that when you take the derivative of a function, you have that dz bar, or partial z by partial z bar, equals d dx. Again, I on the bottom minus I on the bottom becomes I on the top, and you have that. So let's follow this through. Suppose we now take dv df dz bar, and we have 1/2 d dx plus I d dy u plus iv. Okay, this is just f here, and this is just this derivative that I had over there. And what do I end up with? I end up with 1/2. I group the bits which aren't multiplied by I, and I get this. And then I group the bits that are multiplied by I, and I get this. And that's equal to 0. But for that to be equal to 0, that has to be equal to 0, and that has to be equal to 0. But that's nothing more than the Cauchy-Riemann conditions. Let's consider some examples. The first example I'm going to consider is the F1 we had in the last lecture. Let me write it out again. We have that f equals x squared minus y squared plus I 2xy. Okay? And let's apply the Cauchy-Riemann conditions. Okay? So if we do du dx, remember, this is u, this is v, du dx is 2x, dv dy equals derivative of this with regards to y gives me 2x. They're equal. Now let's do du dy. What is that equal to? Well, I have to take the derivative of that with regards to y. I get minus 2y. dv, hang on, dv dx, I get 2y. And again, one has to be equal to this, has to be equal to minus this. Cauchy-Riemann satisfied. So that clearly works. But that's not surprising, because if you remember, when we look at this, if you look at this more carefully, what is this function? What is this function? Well, this function is simply z squared. Let's consider another example. Let's consider the following function. F of x and y equals x cubed plus 3y squared x plus I 3y x squared minus y cubed. Now, remember, this is the u, this is the v. Let's apply the Cauchy-Riemann conditions. We have du dx equals 3x squared plus 3y squared. Now, what about dv dy? It's 3x squared minus 3y squared. Okay, Cauchy-Riemann not satisfied there. Let's just check the other one. Du dy is 6yx, dv dx is 6yx. This should be equal, this one should be equal to minus that one. Cauchy-Riemann not satisfied. So this is not analytic. In other words, you can't express it as an f of z. Now, the Cauchy-Riemann conditions can be used to show that if f is analytic, then u and v are harmonic functions. Okay, what is a harmonic function? Suppose you have a function f. F is our harmonic if you take the Laplacian of it and it's equal to 0. It satisfies Laplace's equation. All right. So this means that you have that if f is an analytic function, then the u and the v satisfy these conditions. To see this, let's just see what happens. Suppose we start off, well, this is a type of proof. Suppose we take du dx, okay, and then take another derivative of that, okay. Now let's apply the Cauchy-Riemann condition. So I've got du dx, and that's got to be equal to dv dy. Okay, but now let's flip the order, dy, and I've got dv dx, and so I've applied the Cauchy-Riemann here, and now I'm going to apply the Cauchy-Riemann again, and I've got d dy d dy of u, and I apply the Cauchy-Riemann again, and so what do I have? I have that this is equal to that, which means that I have d squared u dx squared plus d squared u dy squared equals 0, which is another way, is just the longhand way of writing this. In other words, u is harmonic. And you can show the same thing for v. Now, this means that it's very easy to build analytic functions from harmonic functions, but more interestingly, we can find solution to Laplace's equation by constructing analytic functions. For example, let's build harmonic functions in the following way. Let's take the following function, f of z equals ln of z, and that's equal to ln of the modulus of z plus I times the argument of z, right? But what we've just seen is that f of z is analytic. Well, we've just built it that way, which means u and v are harmonic. In other words, the functions u equals ln of mod z, which is ln of the square root of x squared plus y squared, satisfies. So we've just by hand built a solution to Laplace's equation in 2 dimensions. But even more interestingly is v equals arg of z also satisfies Laplace's equation. And we'll see that this is extremely useful for solving problems with the correct symmetries. It's a really neat way of solving Laplace's equation in 2 dimensions in lots of different situations. Now, we see that the Cauchy-Riemann conditions link u and v. So Cauchy-Riemann link u and v in various ways. I'm going to show you another way in which this happens. Let's consider a function f equals u plus iv, okay? And this is a function on the Argand plane. And I'm going to look at the following surfaces. I've given this function and I want to look at curves which satisfy u equals a constant, v equals a constant. All right? In other words, just to be explicit, this means that I want u, let me go back a bit, just to remind you, u of xy equals a constant, that's a line, v of xy equals another constant, okay? Now, let's find the normal vectors to these curves, all right? So to find the normal vectors to these curves, I've got that n sub u, okay, that's a normal vector, I'm not going to normalize it, so I'll just have an arrow, is going to be du dx du dy. You remember this from your vector calculus. Do the same thing for the function v. dv dx dv dy. Okay? Now let's take the dot product of these two things. Let's do n u dot n v. But if I do the dot product, what do I have? I've got du dx times dv dx plus du dy dv dy. But now let's apply the Cauchy-Riemann condition, okay? And the Cauchy-Riemann condition tells us that this thing is equal to dv dy, and that this thing is equal to minus dv dx. But look at what we get. We get dv dy dv dx minus dv dx dv dy, which is equal to 0. In other words, the normals are perpendicular to each other. Let me just pull that out. It means that the normals to these curves are perpendicular to each other, which means the curves on this two-dimensional, on the Argand plane, are orthogonal. In other words, if we write down isocontours for u and v, they will intersect each other at right angles. Let's look at an example of this. Let's consider the function f of z equals z squared. We've seen this function already. And we've already seen that that means that u of x and y equals x squared minus y squared. And v of x and y is equal to 2xy. Okay? Now, what are these curves? Let's just write them out and let me give it a go. We have that v equals constant, 2xy equals to a constant, are basically hyperbolas like this, depending on the sign of the constant. Right? And what about x squared minus y squared? Well, these are hyperbolas as well. And what do? They do that like this. They do things like this. And the interesting thing is they intersect at right angles. And if they don't look like they intersect at right angles, it's just because of my crappy drawing. But these curves intersect at right angles, exactly as we predicted using the Cauchy-Riemann conditions. Sometimes we're given a part of some function and we want to figure out what the corresponding complex function means or is. Let me just be clear. So we want to figure out what some f of z is, and suppose that we're only given a bit of it. For example, suppose you're only given v of xy, and you want to reconstruct the full f of z, which is u plus iv. Okay? For example, let's suppose that this v of xy is equal to x squared minus y squared plus y. How can we figure out what u is such that f of z is a complex function? And just to make it simple, let's assume that you're also given the condition that f at 0 equals to 0. Well, let's look at this. If you look at this bit, well, that is simply the real part. So the first thing we're going to do is we're going to try and guess it. Okay? And if you look at that, what is that? Well, that's the real part of z squared, right? If you take z squared, what you get x squared minus y squared plus I 2xy, as we've seen again and again over the last lecture and the previous lecture. What about this bit? Well, that's the imaginary part of, sorry, this is confusing, let me erase that. The imaginary part of z is y, okay? So, a good guess would be that f of z, if the real part is going into the v, there's a factor of I there, so we have to multiply it by I, so it's iz squared plus z plus some constant. And then if you set f of 0 equals to 0, that implies that c equals to 0, so we get rid of that. Now, that was an easy one to guess, but what if we try to be more systematic about it? And to be systematic, we use the Cauchy-Riemann conditions. Okay? Well, let's do that. First of all, we want to figure out u. So we know that du dx equals dv dy, and dv dy over here gives us minus 2y plus 1. So if we integrate, we get that u is equal to minus 2xy plus x plus h of y. Okay? And now let's apply Cauchy-Riemann again. So this was Cauchy-Riemann 1. Let's apply Cauchy-Riemann again. So we have du dy is equal to minus dv dx, and that's equal to minus 2x, right? We only have an x here. And we have that du dy is, get this from that, and that, what does that give us? That gives us that that's equal to minus 2x plus h of y. Okay, which means that h of y, if we integrate, we've got, dh, like that. We've got that dh dy equals 0, because that cancels with that gives me 0, so we integrate it, we get a constant. Okay, and so we have that u is equal to minus 2xy plus x plus a constant. But now remember, f of z at 0 equals 0, which means c equals 0, and we recover exactly what we had before, which is u equals minus 2xy plus x, and here v is given up there, and that is nothing more than f of z equals to iz squared plus z. So that's the way that you'll probably do it in many cases. It's always much quicker to guess, but you know that you've got a systematic route to figure out all the bits of a complex function if you're given, or of an analytic function if you're given one of the bits.